Okay, so this talk is about shortest path on convex polyhedral surfaces. Um, so this picture is a convex polyhedron, and we have 2 points on the surfaces. And um, so this red is the shortest path. So we actually study the 2 point shortest path queries. So here P is a surface of a convex polyhedron of n vertices, and we want to pre-process P into a data structure. And so the query is given 2 point ST, and we want to compute the shortest path pi ST, and this length is DST. So our target query time is log n. So this is to compute the length, and you need additional linear time to output the path. That's our target. So here, our previous work and our result. So all query time are log n, I think except one. So we use an O star to hide a factor of n to the epsilon. So previously, Agua and Aronov and Oroka and Shevin, and we call them AAOS. So they give a data structure of n to the eighth space, again, log n query time. So we improve the space to this, so more than linear factor improvement. And we also consider some special cases. The first one is the edge face case. So here only one query point restricted on edges of P, like S is here. So so for this case, the previous work used into the sixth space, and we improve that to this. So less than linear. So another edge case is both query point on the edges. So we give into the 5 space and log n query time. So this particular case was not considered in the previous work, but there's a special case. And so if one query point is restricted, is a given single edge. In that case, Cook and Wang, the given n to the 5 space and log square n query time. So we improve the space by roughly a linear factor and reduce the query time to log n. So if you do this for every edge, then we get this result. Okay. So another problem, a related problem we considered is to compute all shortest path edge sequences. So here we introduce unfolding. So if you have a shortest path, like here, and then so those are the faces intersecting this path, and we can unfold them in one plane, and then in one plane the path from S to T becomes a line segment, which makes sense, right? In the plane, the shortest path between 2 points is a line segment, and and we also know a shortest path cannot intersect each edge more than once, and the path cannot contain any vertex in its interior. And given a shortest path sequence, the path can be reconstructed in linear time by unfolding this path and following the line segments. So here are two questions. The first one is, what is the number of distinct shortest path edge sequences? So amount finally prove that there's a big theta of n to the fourth in the worst case. And the total size of our sequences, I mean, each sequence could have order n edges, and so total size is theta n to the 5. Second question is how to compute all these shortest path edge sequences. Previous best algorithm again takes n to the 6, and so we get roughly linear factor improvement. You see that if we want to output all these sequences explicitly, so this result almost match this worst case lower bound. Okay, so start unfolding. This is the concept introduced in the previous work. So here, if S is a point on P, like here, and the start unfolding, we use the US to denote that. Is to cut the shortest path from S to all vertices and unfold P to the plane, and it becomes a simple polygon. So for example, here, S is in the face of P1, P2, P4, then these three segments are their shortest path. And for P3, P5, we have a shortest path like that. So their star unfolding is like this way. So S will be unfolded. You cut along this red path. So S will becomes 5-point source. We call that source images. So S1, S2, S3, S4, S5. And the other 5 vertices actually is P1, P2, and P3, P. So if you look at here is if you unfold this and then from P1, the next one will be P2, and the next one will be P3, and the next one will be from here to P4 and to P5. That's why we have this order. And this unfolding can be partitioned into n triangles, like here, each white region is a triangle. And each triangle has so as we call that source images. So each triangle has a vertex that is a source image. The other two vertices are the vertices of the P. And this region, this blue region is a kernel. We call that kernel of the unfolding. So given query point T, we actually given query point T in the star unfolding, its closest source image actually determine the shortest path. So if T is in a triangle like here, then this case is easy. So in this case, so the source, the closest source is just S1. But the difficult case if T is in the kernel, in this case, so any source image could be its closest source image. So for example, you could compute the Wang diagram and look at which region contains T. And in this example, this region S1 contains T, therefore S1 is the closest source image. Okay. So another concept is the range trees. So for a point, so the reach points are the points with at least 2 shortest path from S. So reach point form a tree. We call that reach tree. In this example, S is here. So the red segment are edges of the tree, range tree. It has n leaves and square edges at most. So for example, S here, then this will be a shortest path. So the shortest path, any shortest path from S cannot cross any edge of the tree. So if you consider range trees of all vertices, so you have n range trees, and their edges together partition the surface into the fourth region, and we call that reach-free region. So the reach-free region has an interesting property that's used in the previous work. So for each range-free region R, in this example, this green region is R, okay? So the star unfolding US has a fixed combinatorial structure for all points S in R. So what does this combinatorial structure means? It means, for example, here, if S moves in this green region, and then the source images of the star unfolding will be moving, like S1, S2, and those will be moving, but the kernel is fixed. So in other words, P1, P2, P3, P4, those points are fixed. So therefore, this kernel region, but this white triangle will be moving, but their cyclic order, like from S1, S2, S3, S4, S5, those are fixed. So therefore, we say that their combinatorial structure is fixed. For that region, we could use UR to denote the star unfolding. Okay. So then we can use that UR to answer queries for S in R and T in UR. So S could be any point in this gray region now, not fixed. So the triangle case is still easy. So we're going to focus on the kernel case, because the triangle case, again, the closest source image is always fixed. So we're going to use a high dimensional lower envelope structure over source image. So namely each source image, the function, the distance function from each source image define a function, then we compute the lower envelope of these functions. So this takes n to the fourth space and log n query time. So this leads to, because you have n to the fourth regions, n to the fourth free region, and then the total will be n to the eighth space. Okay. So here's our main idea. So the observation is that so the neighboring range free regions share an edge, that is an edge or range tree of a vertex P. And their star unfolding actually differ only slightly. This was discovered in the previous work by Cook and Wang. So for example, here, if this is a star unfolding, so when I move S within R, and those, for example, those 2 points S2 and S3 will be close. And if you move, and these two will be merged into one source image. And then S3 will go in this way, not go this way. So S4 will be a split into two, like here. So those 2 points merge into one vertex source image, and S4 is split into two. But you see the kernel order originally is P1, P2, P3, P4, now becomes P1, P2, P4, P3, P5. So it's changed too. But only these 4 source images get changed. The other n-4 source images do not change. So that's an observation. So therefore, what we do is, assuming we have a data structure dr for R, okay, and we could reuse some information of dr in order to construct dr prime instead of constructing dr prime from scratch. Okay. So that's the motivation of our idea. To implement this idea, what we do is we classify source image as stable and unstable. Like in this example, and these two will be unstable, and but S1 and S5 are stable. S4 is unstable too. So, so therefore, at most 4 unstable, but the remaining are stable. So what we did is we build a global structure for stable images, and we build a small local structure for unstable one. If you have a relatively few unstable source images, so the number of local structures is small as well. So what we do is we're going to define a small region B. We assume B intersect at most this many into the 2/3 ridge tree edges. So in this way, we only have this many source images are unstable, and the rest of them are stable. In the pre-processing, we build a global data structure for lower envelope over all stable images in B. So that still takes into the fourth time. But then we're going to build a local structure per free region inside B. So we know that B has this many ridge-free regions. Therefore, the number of ridge-free, this many ridge tree edges. So therefore, it has this many ridge-free regions. So the data structure of each region now, because it has we only consider unstable source image. It has this many source images. Then you times 4, and that becomes n to the 8/3 for each region. And therefore, the total space is this times this. So you got n to the 4. That's make these two the same. That's why we pick this parameter. So total over all range-free regions in B is now n to the 4th space. So we compare to the AAOS approach, the previous approach, and they have n to the this many regions. If you build a data structure for each region, then the total is this. So you see that. So we see a factor of n to the 4/3. So this is only for, this is only for a small region, but we have an entire surface what we do is we partition P into small regions B, and for each face F of P, we partition F into small regions like B, and then we construct cuttings on the edges of the range-free regions only. In this way, we can prove that the total number of such small regions B is this, n to the 2 plus 2 over 3, and so each B need n to the fourth space, therefore the total space is the pre-processing time is the same, so the query time is log. Okay, so now the edge face case is one query point S is on edges of P. So then we follow a similar idea, but we only focus on the edges when we consider S. So in this way, ridge trees partition edges of P into n cube segments. We call that edgelets. And each edgelet belongs to the range-free region. And therefore, the star unfolding is combinatorial identical for each edgelet. So we construct a lower envelope structure for each edgelet. But this is a one-dimensional lower because the S is restricted on a segment, line segment. So we have n cube space is enough. Again, previous approach, you have this many edgelet and this many space, and the total space is n to the 6. So our solution is again two neighboring edgelet. Their star unfolding only slightly different, and we apply the similar idea. But now you do the cutting on one on a single line, so that's just the partition. So the total space becomes this. Okay. 1 n to the 5 plus 1 over 4. Okay, so we quickly talk about the shortest path edge sequences. Again, edge sequence is the sequence of edges of P crossed by shortest path. For any point S, we're going to define this notation sigma S as the set of edge sequences of shortest path pi st for all t in the surface P. So with a fixed point S. So the observation we find is, or roughly speaking, that this set sigma S is uniquely determined by the range tree of S. So we're going to use this note. So then for each edge E, we define notation sigma E as the set of edge sequences for all S at E and for all other T. So in other words, the first edge of the edge sequence is E. So we can compute sigma E in n to the fourth time. And then if we do that for every edge, then we get n to the 5 time for the for the total time of all edge sequences. So the strategy to compute sigma E is we're going to move S along E. We're going to update this sigma S during the move. And we find that sigma S only gets updates if the ridge tree changed topologically. So we find there are two types of topological changes, which we're going to show next slides. So then we design algorithm to keep track of all topological changes. So the total time is k log n, but k is the number of changes. So we prove that k is at most O star n to the fourth. So this is probably the most challenging part of the paper to prove this upper bound. So with this upper bound, we get this time. Okay, so briefly, two types of topological change. So one type is if you have two vertices in the tree, and then if you move S, so these two vertices getting closer, and finally they merge, and then they split into two. So that's the first type of change. The second type is you have a vertex on this face, V, and then if you move S and V were getting closer to V prime, and then V is here, and then V cross to the next face. So this is the second type of change. We're going to show some one highlight to prove this lemma. We introduce a new unfolding with respect to edges. So basically what we do is, E is here and E prime here. If you consider shortest path for all possible point of S in this edge and T in E prime, and then we consider all possible shortest path. If you unfold all faces intersecting all this shortest path, so we can get unfolding that into a plane that containing E prime. So the key property we can prove is there's no shortcut in the unfolding. Which means for any image S prime of S and any point T of E, the length of their line segment in the unfolded plane is no shorter than the length of their shortest path. So using on this unfolding, we prove this key lemma. Finally, the edge case. So when both query point are on polyhedral edges, and then we use the result of our analysis for the shortest path edge sequences, and also we use persistent trees. We got into the fifth space and the log and query. Okay. Okay, thank you for your attention.